Hello everyone, and welcome to the latest edition of Journal Club. Thank you so much for joining me. My name's Robert Palgrave, and this is Journal Club, the Twitch channel. Very warm welcome. I'm just having a look at my sound levels. I'm not entirely happy with my sound levels. I'm going to increase my my microphone level a little bit. Maybe I need to sit a bit closer to the microphone. How are you guys doing today? Good to see you all. Thanks so much for joining the stream. As I do on the start of most streams, I'll explain a little bit about what Journal Club is, because we're very new. We're very new. We're so new. So what Journal Club is, it's a Twitch channel where we discuss scientific papers. So what is a scientific paper, if you're not familiar? A scientific paper is the way that the scientists talk to each other. The way that they communicate, the way that they tell the world about their findings. After they've finished doing their experiments, or their observations, or their calculations, they write it all down. Write down everything they did, write down everything they found out, write down everything they think it means. That part may be right, part may be wrong. And they put it all together in a paper. So they write a manuscript, they put it all together in a paper, and they send it off to a journal. And the journal has got an editor. That's a very important person. That editor will read the paper, and they'll think, well, is this paper worthy? Is it worthy of my journal? Is it worthy of being published in my journal? And if they think it might be, then what they'll do, they'll send it for peer review. So peer review is the process where other scientists who are completely unrelated to the original group who did the work, other scientists will read it, and they will basically nitpick. They will find anything they can which is wrong with it. But really what they're doing, they're checking that the science that's being presented in that paper is reasonable. It's probably correct, or has a chance of being correct. So it's not complete nonsense. Now sometimes that process doesn't work very well, and sometimes the papers get past that stage, even though they are complete nonsense. When I say sometimes, I mean most of the time. Okay, it's not that bad. Maybe not every paper is nonsense, but many papers get past peer review. That's the part where the other scientists kind of check on the work. Many papers get past that point, even though they are nonsense. But actually, to be fair, peer review that's not really the point of peer review. The peer reviewers, the checkers, they can't check everything. They can't go and do all the experiments again. They can't just repeat everything to see if it's correct, because otherwise you'd just spend all your life doing that. That would be your whole life. And the peer reviewers themselves, so they're scientists, they want to do their own work, they want to make their own discoveries. So they normally, they might spend a day, they might spend 2 days, but they're not going to spend weeks and weeks checking this manuscript. So they just check whether there's anything obviously wrong, anything completely stupid, anything that just doesn't make any sense. They also have many peer reviewers tend to spend a lot of their time correcting language and grammar, which really kind of isn't their job, but seems impossible to stop them. They love doing it. I guess if people are pedantic, if they're pedants, they quite like correcting anything they see that's wrong. So if they see some grammar that's wrong, they're going to change it. If they see a sentence construction that isn't entirely to their liking, they may ask you to change that as well. But anyway, once the peer reviewers are happy, if they ever are, and there's more than one of them, so you've got to make them all happy at the same time. Once the peer reviewers are happy, then they write back to the editor of the journal, remember, the very important person, and they say, we think this paper's fine, you can publish it. And then the journal publishes it. Well, they don't. Okay, then the journal says they will accept it, and then many journals will say, now you need to pay to the original scientists. So the scientists who wrote the paper then have to pay to have their paper published, which is kind of surprising maybe to many people who are not actively involved in scientific publishing, that actually the journals, you might think if you write an article and someone publishes it, they will pay you. That seems normal, yeah? If journalists who write for newspapers get paid to write articles for the newspaper. but not in scientific publishing. It's the other way around. The people who write the articles do all the work. They write the paper, they send it to the journal, and then they pay the journal to publish it. So why is that the system? Well, that's probably beyond the scope of this stream. But maybe one day we will have a stream on journal publishing ethics, the past, present, and future. How good or bad that system is, and how maybe it could be changed. But I think that's not this stream, because I probably have to work out what I think, and I haven't done that yet. Because I wouldn't just want to talk nonsense. That wouldn't be something I would want to do. Speaking of not talking nonsense, or speaking of talking nonsense, what is this stream about? Well, this stream is for talking about journal articles, so talking about papers that have been published by scientists. So all the papers we talk about have gone through that process. They've been written by the scientists, they've gone to the editor, they've gone to the peer reviewers. The peer reviewers have, maybe said change some stuff. The original authors have changed the stuff, and then finally the peer reviewers have agreed, and they've gone into the journal. And that's what we're going to be reading. We're going to be reading the end product of that long process, maybe involving many people, many very smart people, and lots of money to pay for the science, lots of money to pay for the paper to be published, lots of maybe not money, but lots of value contributed by the peer reviewers, who are basically work for free as well. That's the other thing, the peer reviewers don't get paid. The people who actually decide whether the article is good enough, they don't get paid either, not by the journal. Most of them will have another job, but they just kind of do that for free because they're such nice people. But anyway, yeah, we're not going to do a stream on journal publishing ethics today. But maybe in future, if you would like to see that, then you can make your views known on that or any other matter by typing in the chat. There is a chat box right there. Apparently, if you type in the chat and press enter, then your message will be posted to everyone. So you can make your views known about that. So what are we doing today? We are talking about a paper, as we do every stream. We haven't had a stream for a while, maybe about a week or so, just over a week. So sorry if you guys have been missing out. I know that maybe you've been missing your dose of Journal Club. In which case, hopefully today will satisfy you. So what are we talking about today? Well, we are talking about, if I can get the right button, we are talking about this paper here, which is in this journal here. This journal is called ACS Materials Gold. So you see this little gold symbol up here, AU, it's the chemical symbol for gold. That is to signify that these papers, every paper in this journal, is gold open access. Gold open access means that the paper is free, completely free for anyone to read in the whole world. If you guys follow the link to this paper, then you will be able to read it yourself for nothing. You don't even have to subscribe, you don't have to give me your personal details. You can even, if you want to, reject the cookies. You can reject the cookies and you will still be able to read this article. And what's more, you can even reproduce this article. You can even post this on your own website. You can even make a Twitch stream that discusses this article and shows it live in the stream, and you probably won't get sued. But we're doing, we're trying to find out as we speak. So how do you get to this article? I hear you all, thinking to yourselves, if not actually saying. Well, luckily, we have a chatbot command, a chat command, to give you the link. Now, sometimes, if you guys have watched this stream before, sometimes you'll realize at this point, I realize that the chatbot does not do the thing that I want it to do. But anyway, let's try it. The way to make this work is you type !paper, no space, !paper, hit enter. I've done it right now. And what it should do is give you a link to the paper that we are discussing. So if at any point you want to follow along, on a different browser tab, don't close this tab, but you can open a new tab or a new window. You know, I'll let you make the decisions yourself. I'm not going to micromanage you on this. And you can click that link and you will be able to read along the paper on your own. So without further ado, I think I've spent enough time on a kind of introduction. Let's have a think about this paper. So this paper is called Magic Size Semiconductor Nanostructures. Where does the magic come from? So unlike many of the papers, in fact probably every paper we've looked at so far has been an actual research paper, so we've been reporting new results. But this, for the first time on Journal Club, is a perspective paper. So what is a perspective paper? It's basically a kind of review article. So it's kind of a paper where the authors are not reporting new results necessarily, but they are summarizing the results in a particular scientific field. So they're giving their views about, you know, what the trends are, what the new things are, what the opportunities are for the field, and putting it together in an article. And these are really nice kinds of articles to read, especially if you are just getting into a new kind of research area. If you may be starting a new project, maybe you're starting a whole new research position, or maybe you're just interested in a particular kind of particular field. These perspectives, these review articles are very, very handy to get you up to speed quickly. The good ones are. If they're written by people who know what they're talking about, then you know they can be incredibly useful. So this particular one is a perspective article. It's on magic-sized semiconductor nanostructures. So we've had a few streams about nano. Nano's been a trend, hasn't it? Nano's been a trend for a long time. You know, probably the whole time I've been in science, which is maybe longer than you might imagine. But it's quite a long time. But I think ever since I've been in science and before, nano has been a bit of a kind of buzzword. But from a chemistry perspective, I'm a chemist by training. I did my degrees in chemistry. I still would think of myself as a chemist. From a chemistry perspective, nano is maybe a bit of a hype word, without, you know, maybe without that much substance. So chemistry is really the original nanoscience, I would say. Chemistry is the original nanoscience because it deals with very, very small things, and that's what nano means. Nano means very small things. But within this context, you know, molecules, atoms, of course, are below nanoscale. They're much smaller than nanoscale. But molecules that chemists tend to deal with are for the most part, nanoscale objects. So chemistry's been a nanoscience for, you know, before people use the word nanoscience. But the kind of hype around nano at the moment, or for the last maybe 20-30 years, is making objects on that scale, on the nanoscale, and controlling matter, being able to arrange atoms, molecules, on that kind of scale to produce new effects, new materials, new devices, new drugs, new treatments that don't exist in nature, that don't exist in naturally occurring things. So I think that's the kind of hype around nano, and there's a lot of good reasons to think that nanostructures, nanoscience, nanotechnology has got a bright future. There's a very famous lecture given by Richard Feynman, who was a Nobel laureate, called "There's Plenty of Room at the Bottom." There's plenty of room at the bottom, and that was his. I don't know what year it was in. If I'd been prepared, I would have researched that. I don't know what year. Maybe I'll find out. Maybe I'll find out while I'm talking to you. There's plenty of room at the bottom. 1959. Oh, a long time ago. 1959. So the subtitle of it is, of that lecture, "There's Plenty of Room at the Bottom, an invitation to enter a new field of physics." So this was a lecture given by physicist Richard Feynman, as I said. at Caltech on December 29th, 1959. So Feynman, I'm just reading from Wikipedia here, which is also CC, OpenCC, so you know, I don't think they can sue me either. Feynman considered the possibility of direct manipulation of individual atoms as a more robust form of synthetic chemistry than those used at the time. Well, Richard, I think you'll find chemists actually have a pretty good idea about manipulating individual atoms. So I think that part of the of his kind of discussion, that chemistry is really kind of unnecessary. We can just pick up atoms and move them around. I don't think that's really in the kind of 50, 60, 70, 60 years since then. I don't think that's really come to pass. We don't do chemical synthesis by picking up atoms and arranging them individually. It's just too time consuming. But I think that the ideas there kind of directly feed into nanotechnology and nanoscience, that kind of thing. So yeah, nano's been a bit of a hype word for a long time. And why are nanomaterials, nanoparticles, nanostructures, why are they different? Why are they different to kind of to regular stuff, to non-nano stuff, or even to normal chemicals? So I kind of say chemistry is the original nanoscience. Well, I can say a few words about that before we get into the paper. Really, the reason why nano is kind of interesting, there's a couple of reasons. Firstly, if you make something nanoscale, you make it very, very small, then you make the material all about the surface. So as you make particles smaller and smaller and smaller, so if you start off with a huge rock and you start smashing it down into smaller rocks, and smash those into smaller rocks, and smash those into smaller rocks, the surface area that you have gets bigger and bigger and bigger and bigger with every smash. With every step of that process, you're making the surface area bigger and bigger and bigger. So anything which happens at the surface, or any properties that the surface has, get increased more and more as you smash this stuff down. And if you take that to the extreme, if you smash the rock, you know, a huge boulder, smash it until it's nanoparticles, so nanoparticles are a billionth of a meter, on the order of size of a billionth of a meter. So it's normally a billionth of a meter is 1 nanometer, so maybe, you know, nanoparticles might be 10 or 100 nanometers. There's all these kind of artificial definitions that don't make a massive amount of sense. So if you break the boulder down into nanoparticles, then anything that happens on the surface becomes more important, happens more. Yeah, so things that happen on the surface happen more. So that can be important for things like, maybe not for breaking down boulders, but things that happen on the surface. For example, the obvious one is heterogeneous catalysis. So catalysis, chemical reactions that happen on the surface of things. If your catalyst is nanoscale, there's a lot more surface, so you can have a lot more catalysis. So that strategy has been used for many years to make more and more efficient catalysts. But so that's one reason. I think one reason is more surface. Second reason is that as you make things nano, you start to get down to the scale. Let's say it this way: you get down to the scale of electrons within the material. So as you break a solid down, it's normally a solid. It doesn't have to be. You can have nano liquids, but normally it's a solid. If you break the solid down smaller and smaller, you get down to sizes which are about the same size as the electron. So what I mean by that, well, you get down to the kind of size where the energy levels of the electrons are affected by the size of the particle. Maybe that's a kind of good way to say it. So when particles are very, very large, they're so much bigger than the kind of interaction volume of the electrons that it doesn't really matter what size they are. Yeah, you can make a bit of metal bigger or smaller. It doesn't really change the way the electrons see it. But if you take a bit of metal, say gold, you make it very, very small. Now suddenly the electrons can kind of see the edges. You know, you imagine you're an electron in a lump of gold, and you can kind of see the edges of the gold. You can see edges everywhere you look because it's nanoscale. That's going to affect the properties of those electrons. And it does. If you take gold and make it nanoscale, you get a completely different material to the normal gold that you may be used to on the what you could call bulk gold or macro scale gold. You know, so nanoscale gold, you get completely different colors. For a start, you can make it soluble. You can make it kind of dispersed in water with the right kind of chemicals on it, with the right surfactants. You can't dissolve normal gold in water, so that's one thing. You can also make change the color, so you can get all sorts of different colors which depend on the size. You can get red and purple, and this actually used for a long time. So this was used back in the ancient world to put color into things, or in medieval times put color into stained glass windows. There's good examples in museums all around the world that will have this kind of coloration in it. Of course, they didn't know that they were gold nanoparticles in that sense. First person I think was Michael Faraday, actually, to suggest that the color from gold colloids, from gold nanoparticles, actually is because of the size, which is, you know, a remarkable observation. He lived in the 19th century. He didn't have access to many of the techniques that will be discussed in this paper, so he couldn't know this for sure, but he was able to suggest or predict or guess or infer that the size, the color of the nanoparticles comes from size. So that is one example. There's loads of properties of materials that change with size, especially nano size. So that's a very attractive field for people to work in, because you can make new materials or change the properties of materials to give completely different effects. You can come up with new technologies, you can come up with new devices, new healthcare treatments, as we kind of discussed before. I've spoken for enough time, I think, before even getting to the papers, at least any further than the title. So let's dive in. Let's have a little look at the abstract. And then we'll start reading through, and I will make some other comments as we go through. Don't worry, it won't just be me reading aloud. I will make some comments as we go through and maybe discuss some points. And if you guys if you're watching live on Twitch, welcome. If you want to make comments along as we go along, if you want to ask questions, feel free to stick that right in the chat, and I will do my best to answer you, or at least, I mean, I will respond to you in some way. I'm not going to ignore you. So feel free to do that. And yeah, let's begin. So let's just go back to the title: Magic Size Semiconductor Nanostructures. Where does the magic come from? So we'll try and understand what this idea of magic size nanostructure. We haven't talked about that at all. We've talked about what nanostructures are, why it's important, but we'll talk about this magic size thing. And it's from these authors: Serena, Busatto, and Celso de Mello, Donega. Probably terrible pronunciation, I apologize to them, but these are the authors. You can check out the paper by following the link !paper. You'll also be able to get, I'm sure, find out more about the authors if you want to Google their names, or there may well be links on the journal page when you get there. Okay, let's have a look at the abstract, which is a summary of the article. The quest for atomically precise synthesis of colloidal semiconductor nanostructures has attracted increasing attention in recent years, and yet remains a formidable challenge. Okay, so colloid is just another word for kind of nanoparticles dispersed in something, so normally dispersed in a liquid, dispersed in a fluid. Nevertheless, atomically precise clusters of semiconductors, known as magic size clusters, MSCs, are readily accessible. Ultra-thin one-dimensional nanowires and two-dimensional nanoplatelets and nanosheets can also be categorized as magic size nanocrystals. Further, the magic size growth regime has been recently extended into the size of colloidal quantum dots. So I don't define quantum dots, but I'm pretty sure that's what that means. Nevertheless, the underlying reasons for the enhanced stability of magic size nanostructures and their formation mechanisms remain obscure. Okay, well that's pretty interesting, isn't it? In this perspective, we address these intriguing questions by critically analysing the currently available knowledge on the formation and stability of both MSCs, which is magic size clusters, and MSNCs, which is magic size nanocrystals, 0D, 1D and 2D. But not 3D. Okay. We conclude that research on magic size colloidal nanocrystals is still in its infancy, and Whoops, let's go up. And many fundamental questions remain unanswered. Nonetheless, we identify several correlations between the formations of MSCs and 0D, 1D, and 2D MSNS. MSNS, I think that should be magic size nanocrystals. Maybe S means structures here. They've kind of changed this. They changed this acronym halfway through. Unless I missed out a definition somewhere. I don't think I did. From our analysis, it appears that the magic originates from the complexity of a dynamic and multivariate system running under reaction control. Well, I mean, if there's any way to kill the magic, that sentence kind of kills the magic, doesn't it? I'm being silly. It's a great sentence. I think they've expressed it very well. But just the contrast of magic with dynamic and multivariate system running under reaction control, I don't know, it's kind of jarring. Under conditions that impose a prohibitively high energy barrier for classical nucleation and growth, the reaction proceeds through complex and dynamic potential landscape, searching for the pathway with the lowest energy barrier and thereby subsequently forming metastable products as it jumps from one local minimum to the next until it eventually becomes trapped into a minimum that is too deep with respect to the available thermal energy. The intricacies of this complex interplay between several synergistic and antagonistic processes are, however, not yet understood and should be further investigated by carefully designed experiments combining multiple complementary in situ characterization techniques. Okay, what an awesome abstract that is. Yeah, that's I think does a number of jobs very, very well there. I think they tease a lot of the conclusions they're going to make in the article, but also they highlight there's lots of stuff that we don't know. Yeah, there's loads of questions which are remain unanswered, as they say, and I think that kind of draws people in. So if you're reading that, if you're thinking of getting into this field, if you're thinking of I want to do some research on a particular research question, I want to contribute something to this field, this kind of article, at least from the abstract, at least what it's kind of advertising it's doing, this kind of article should be exactly what you want, because it highlights what's known and, crucially, what the unknown things are, what are the problems, what are the questions, what are the challenges in this field. And that will be incredibly valuable, I think, for anyone wanting to work in this field. All right, really well written abstract. I love what they've done there. I was kind of making fun of the juxtaposition between magic in inverted commas and then this highly technical sentence which came on after that. But I think it actually does a good job of piquing your interest. It's kind of to me it seems like a funny joke the way that they did that. So I think that's excellent. Great. All right. Shall we start with the introduction? Let's scroll down a little bit. Right, colloidal introduction. Colloidal semiconductor nanocrystals are versatile nanomaterials whose optoelectronic properties are determined by their size, shape, composition, and compositional profile. Yeah, so that's kind of the key thing, as often happens in these streams. The author's explaining in one sentence what I've spent 20 minutes at the start rambling on about. It's the fact that a material's properties depends on the size and shape of the material. That's what nano is all about. When you get down to nano regime, that's what happens. The properties depend on the size and shape, which gives you a lot of extra levers to control. If you think of gold is a good example which you always go back to. Doesn't matter what shape you make gold into, doesn't matter what size a lump of gold is, it's still going to have basically the same properties when you're on a macro scale, but when you go to nano scale, properties change completely. Okay, the size and shape dependence of their properties emerges from the spatial confinement of charge carriers and excitons in the material, resulting in quantum confinement effects. Yeah, that's kind of what I said as well. So the electrons, the size of the electrons, the interaction volume of the electrons becomes basically the same as the size of the particle itself, and so that has all sorts of effects. And I've got a nice figure 1 down below which will show this. The impact of these effects is determined by materials dependent characteristic length scale given by the exciton Bohr radius. So that, in a way, you can think of that as the size of an electron within the material. for some definition of size. Again, physicists, anyone wants to come in and make a comment on that, give a different opinion, that's fine as well. But yeah, I think it's to an approximation, it's the size of the electron, which ranges from 2 to 50 nanometers depending on the semiconductor, figure 1. The degree of quantum confinement may vary in different directions depending on nanocrystal shape and size, yielding 0-dimensional quantum dots, 1-dimensional nanowires, and 2-dimensional nanosheets. Quasi 1-dimensional, i.e. weak confinement, occurs also in the length direction, e.g. nanorods, and quasi 2D, e.g. weak confinement, occurs also in the lateral directions, e.g. nanoribbons and nanoplatelets, can also be prepared. Okay, let's have a little look at figure 1. Figure 1 is a nice figure, I think. Yeah, so here they're showing in the top left in panel A, they're discussing electronic structure, arrangement of electrons in a material. So here they have something which is kind of like a macro scale material, although it's actually very small. So let's draw our own version. Let's extend this this diagram and draw our own version of it. Can I choose red? This is radical. And we're going to draw. Yeah, let's draw the valence band down here. So I'm extending their diagram. So this is, do I have text on here? I don't have, oh, I do have text. Look at this. Look at this, I do have text. Valence band, let's make this red. Oh, I can only choose 4 colors, that seems a bit. Valence band. Conduction band up here. What color can I make it? Blue, there we go. I only need those colors, they knew what I needed. So in the non-nano material, so let's say, what should we make this? Let's call this 1,000 nanometers. I don't know why I didn't use text. That would have been a lot easier, wouldn't it? 1,000 nanometers. 1,000 nanometers. Oh man, this is terrible. Let's rub it out and use text. Yeah, I'd be very interested to see some research on why writing with a mouse is so difficult. Because you think you should be able to practice it. Yeah? Why is writing with a pen easy and writing with a mouse just cripplingly difficult? Maybe I just don't practice enough. Right, let's say 1,000 nanometers. I'm going to make this text a different color. I'm going to make it black. And we're going to move it. There you go. So now we've kind of extended their diagram. So this is over here. This is macro scale. This is bulk. You could say large scale particles, and you have a valence band and conduction band. The valence band, of course, let's go red. The valence band is filled with electrons. So this is kind of shaded in here. The valence band is filled with electrons. The conduction band normally empty if it's a semiconductor. The conduction band's got no electrons in it. And the gap between, let's choose a different color. Let's go black. The gap between is the band gap of the material. So the band gap determines a lot of properties. Determines conductivity for a semiconductor. The band gap, it's the energy gap between them. So if you want the material to conduct electricity, you have to move an electron from the valence band up to the conduction band. So the more energy that takes, the less conductive the material normally is. There's exceptions. We're not going to go into too much semiconductor theory. But also it determines what the material looks like. If you have a very wide band gap, then the material won't be able to absorb visible light. It will only absorb ultraviolet light. So it will look it won't have a color. It will not absorb any visible light at all. But if the band gap is narrower, then you start to get colors coming in because the material can absorb some visible light. But not all of visible light. So that's how you get colors. When you make the band gap very narrow, then it can absorb all the visible light, and so the material will appear black. So the band gap determines things like conductivity, but also color, loads of other things as well. But we won't go into that. So when you have a bulk material, a large scale material, if it's a semiconductor, you might have an electronic structure like this. But as we make it more nano, so even 6 nanometers is pretty nano. 6 nanometers is pretty nano. You get this stuff happening. So what is this? This is this whole concept is called quantum confinement, and that's where the the band, which are kind of a load of overlapping electron orbitals, start to not quite be so overlappy, not overlap so much, and they tend to break up into localized orbitals, or localized is a good word, localized or discrete or non-degenerate or not overlapping. Not overlapping is a good word as well. So these are kind of individual orbitals which aren't really overlapping very much anymore. And also you'll notice that the band gap, which is this energy, gets bigger and bigger as we make the particles smaller. Band gap gets bigger and bigger, as they show here, and even bigger. And so what does that do? That changes the color. I just mentioned to you that the band gap determines the color, and so as we change the size, the color changes. And these are I think these are luminescent colors. I haven't read the under UV. Let's scroll down. Under UV illumination, yeah. So these are kind of the luminescent colors which are coming off these nanoparticles in different sizes. And the same material, which is changing the size, gets you all of these different colors as described, because the band gap is changing size. So you get this quantum confinement. That's where the orbitals go from being very delocalized in the bulk material to very localized, and eventually let's go down the other end. As down here we'll have, let's draw, this is an atom. This is a good thing about Creative Commons licenses. You can just change the work. You can adapt the work yourself. So let's do that. Let's put atom here, and then let's draw on what the orbitals would look like. Let's go with red. Let's go red. So in the actual atom, we wouldn't have any overlap at all. We wouldn't have any delocalization at all. We'd only have these individual orbitals which go up like this, and then above we would have the unfilled orbitals. Let's make them this color. Whoops. Above we would have the unfilled orbitals. So the red are the filled orbitals, the blue are the unfilled orbitals, and we wouldn't have any overlap. See, even in this 2 nanometer one, there's a little bit of overlap of orbitals down here. Here there's none at all. They're completely quantized. They're atomic orbitals. They're just the orbitals that occur in an atom. So there we go. We kind of extended their diagram to the macro and down to the atomic scale, which is kind of good. Okay, so this is the as I said, one of the most important effects of nanoscaling things, making things nano, is that you change the electronic structure of them in this way. And here they're showing also how you can change the electronic structure, the DOS, density of states, or the DOS, going from a bulk semiconductor. So this is what we have here, to a 2D, a 1D, a 0D. 0D is these particles down here. You end up with these kind of discrete energy levels, like we drew for the atom. I think these are ways to stabilize. Let's just see what it says about this. I think these are ways to stabilize nanoparticles. That's another thing we didn't touch on at all, stabilizing nanoparticles. So why is nano difficult? One of the reasons nano is difficult is because nanoparticles normally really do not want to be nanoparticles. Yeah, if they're given a choice, you have 2 nanoparticles next to each other, you're given a choice, they are going to want to stick together. They're going to want to stick together because the surface of anything is a region of high energy. So surfaces normally, for most things, if you stick surfaces together, that becomes lower energy system. That's a more energetically favorable, that's a more stable arrangement because you have less surface. So what I said earlier about surface area increasing as you make things nano, actually that leads to an increase in the energy, because the surface is a region of instability. And if given a chance, the material will spontaneously decrease the surface energy by decreasing the surface area by sticking particles together. So if you want your nanoparticles to stay nano, you're going to have to stop them sticking together, and the main way that you do that is with this thing called surfactants. So you put these molecules onto the surface of your material, and they physically prevent the nanoparticles touching each other. Yeah? So these molecules adsorb, so they chemically bond to the surface, and when they do that, they stop the particles actually joining together, and they keep them nano. So that's a really essential part of nanoscience. If you're working with nanoparticles, especially in solution, you're going to have to somehow prevent their aggregation, and normally that's through this idea of surfactants. Right, let's change up the music a little bit, get a little bit more energetic, hopefully, because we've got a long way to go. We've already had 45 minutes of the stream. We haven't really gone into the paper yet, so I'm going to try and accelerate a little bit. We've discussed a lot of the background topics, so let's see what the main points are going to make. Right. Another important characteristic of colloidal semiconductor nanocrystals is that they are coated with a layer of organic ligand molecules. I just said that. The ligands have a crucial impact on the properties of colloidal nanocrystals, defining their size and shape during the synthesis and their post-synthetic colloidal stability. As a result, one can take full advantage of nanoscale effects to combine property tailoring through size, shape, and composition control with easy surface functionalization and solution processing. This prospect has turned colloidal semiconductor nanocrystals into attractive materials for several existing and emergent applications. However, the realization of this bright potential has been hindered by both the intrinsic toxicity of the best developed colloidal nanocrystals, which are based on cadmium and lead chalcogenides. Cadmium and lead both pretty toxic, and the relatively large polydispersity of ensembles of nanocrystals of alternative semiconductors. Okay, so the best nanocrystals in terms of the ones that we can make in the best way with the most uniform properties and the best control over the sizes are unfortunately made of these toxic things, cadmium and lead. If you go to non-toxic things, they are less good. Yeah, so we have less control over their size. Maybe we have less control over they're less uniform. Yeah, they're less reproducible. Maybe that's kind of what they're saying there. This has driven both the development of alternative colloidal nanocrystals based on non-toxic or less toxic elements, for example, indium phosphide, indium antimonide, copper, ternary copper with two A and X, where A are anything, indium gallium, and sulfur and selenium, and a quest for atomically precise synthesis yielding monodisperse ensembles of nanocrystals. When they say ensembles, they just mean a group of them, yeah? So you don't just make one nanocrystal. So despite what Richard Feynman was saying, he's a physicist, he didn't really know about this stuff. You're not just going to assemble the atoms on one nanocrystal, yeah? You spend your whole life making, I made one nanocrystal, okay, great. People who work with nanocrystals work with billions and billions and billions of nanocrystals that they make all at the same time. Yeah, so that's what they're calling an ensemble of nanocrystals. You don't just make one. Okay, Richard, you don't just make one. In this perspective, we address topics that are relevant to the latter, which remains a formidable challenge. So the latter, just to remind you, is this atomically precise synthesis. So what do they mean by atomically precise? Well, actually, maybe this does kind of address the Richard Feynman challenge. Chemistry can be messy. Chemistry, you don't get 100%. If you're making a molecule, you don't get 100%, of that molecule. You get some other impurities in there. If you're making nanocrystals, you don't get all of them exactly the same size. They come out of different sizes, often. But what this paper is about is this idea of atomically precise synthesis, and that's where we aim to, or try to get, an ensemble of nanoparticles where they are all exactly the same size. So by exactly the same size, I mean that they have the same numbers of atoms in each nanoparticle, which is actually pretty out there, pretty ambitious target to try and make these particles with the same number of atoms in them as each other. But that's what this article is about, these so-called magic numbers of atoms, that people have found that a magic number, a particular number of atoms happens to be particularly stable, happens to be very, very stable. And so it's actually possible to make these kind of magic number nanocrystals. And that's an easier way to synthesize this with atomic precision. Yeah, so it's definitely picking up the baton that Richard Feynman put down in that lecture we talked about at the beginning. That lecture on There's Plenty of Room at the bottom. So atomic precise synthesis is still beyond reach for colloidal semiconductor nanocrystals, despite promising recent advances for cadmium selenide quantum dots. Okay, a couple of papers there may be interesting, but is nonetheless already routinely carried out for a class of materials known as magic size clusters. There we go, MSCs. The term magic size cluster is used to denote atomically precise clusters of metals or semiconductors characterized by a well-defined number of atoms and a higher stability than a slightly larger or smaller clusters. So that's the key thing, yeah. The magic of the magic size nanoclusters is that a particular number, so for example, I think gold 55, so 55 gold atoms all together in a cluster is particularly stable. I think it's 55, I might be wrong, it doesn't really matter. 55 gold clusters together is particularly stable. 54 or 56, you kind of lose the magic is gone. You lose the magic. So what that means is all of the particles that end up, just being 54 atoms or 56 atoms, they're going to change to be 55 atoms. Yeah, so they're going to grab an atom from somewhere, or they're going to kick an atom out in order to become 55, because that's the most stable arrangement. Yeah, that's the magic number. So yeah, the question, why is 55 a magic number? There's other numbers as well. I can't remember what they are. For gold, why is it different for different materials? What's going on there? That's something that if we could understand, maybe we could kind of control that a little bit more. Maybe we could get more towards atomic precision with some semiconductor nanocrystals. Okay, so magic size. What was MSC? Magic size clusters. Sorry, magic size clusters of semiconductors have been implicated as intermediates in the formation of colloidal nanocrystals through non-classical nucleation and growth pathways. However, for reasons to be discussed in more detail below, their exact role is still under intense debate and seems to vary depending on the system conditions, resulting in conflicting reports. Furthermore, the stability and growth mechanisms of semiconductor MSCs, magic size clusters, are still poorly understood despite several decades of extensive research. MSCs grow in discontinuous and quantized fashion in discrete jumps from one magic size to the next, without the appearance of intermediate sizes, in striking contrast with the continuous growth regime typically observed for colloidal semiconductor nanocrystals. Super interesting. Okay, so they're saying that in kind of classical particle growth, in fact I think they've got a good figure for classical particle growth down here. So for classical nucleation and growth, you get this kind of energy level diagram, okay, or any energy pathway diagram. So you start off with what they call monomers, or the building blocks of your crystal are dissolved in solution. Yeah, they're dissolved in solution. What has to happen is in order for these individual monomers to form a particle, they need to start sticking together. But the problem is, as they start sticking together, it's actually energetically favorable for them to, as soon as they stick together, to actually break apart again. So the energy, as you start to increase the cluster size, the energy, this is classical nucleation theory, the energy of that cluster increases. So this is delta G, gives free energy. The free energy of that cluster actually increases. So that's unfavorable, yeah? So chemical systems, physical systems want to go downhill on this energy diagram. They want to roll downhill. They don't want to go up. If they go up, you have to put energy in to make them go uphill. It's like pushing a boulder uphill, yeah? If you get to the top of a hill and push it down, it will just go by itself. But to get it back to the top, you're going to have to put a lot of energy in. Okay? Same with this. So the monomers, as they start to form the critical nucleus, that's an uphill process. So you have to push this boulder up this hill to make this particle. Once you get to a certain critical size, which is this size, then further addition of monomers is actually now a downhill process. So it's an energetically favorable process. So further addition of monomers, further growth of the particle, is downhill again. And that's what I said before. Then the particles want to get bigger and bigger and bigger because they want to reduce the surface energy. Yeah, as we talked about that before. However, how do you get past this initial hump? You need to have enough energy in a system to push it uphill, and then for it to roll over the top and then start growing spontaneously on its own. But this formation of the critical nucleus is kind of the key point in classical nucleation theory. This is kind of an activated process. Yeah? So you need to put in energy to get this process started, and then once it's started, it's going to be spontaneous. It's going to happen on its own. Yeah. Now, without jumping the gun too much, but we do actually need to make some progress through this article. This is what they're now showing as non-classical nucleation. You can see we have a slightly different energy level profile here. We start from the same place. We start with an uphill process to grow the particle size, to go from a monomer to a nucleus, to a solid nucleus. But then there's this kind of intermediate here. So an intermediate on this energy level diagram is where you kind of have a dip, where you have a little kind of shallow basin. So what happens if the system gets stuck in here, is actually energetically unfavorable to get smaller, to go this way to get smaller, and it's also energetically unfavorable to get bigger. So whichever direction it goes in, it actually costs energy to do that. Or another way of saying it is that this is a stable, or at least metastable, locally stable cluster size. So changing this cluster size in either direction, bigger or smaller, is energetically unfavorable. So this cluster size can exist for maybe quite a long time. And this is the idea of these magic size clusters. Yeah. So when you have this kind of non-classical, let's rub out some of this so it's a little bit clearer. When you have this kind of non-classical nucleation theory, you can have these transition states, these intermediates, this cluster intermediate. That's this guy here, which is just the right size on this energy level diagram that it doesn't want to, it costs energy to get bigger or smaller, so it's happy to stay the way it is. Contrast that here. If you took a particle size here, it costs energy to get bigger, but it's actually, if you let it go, it will rather roll downhill and turn back into the monomers again. Yeah, this one won't. If you let it go, it just stays there. So imagine it's kind of like a marble on a surface. Yeah, if you drop this one here, it's just going to stay where it is. If you drop this one here, it's going to roll back down here. Or if you drop this one here, it's going to roll back down here. This is the idea of magic size clusters. Okay, the question is why? Why is this size stable? What's the chemistry? What's the physics? Which is keeping that particle stable at this size and not any bigger, not one atom bigger, not one atom smaller. Right. Let's go back to where we were, which is quite far back. So interestingly, the confinement dimension, i.e. diameter or thickness of ultra-thin colloidal nanowires, nanoribbons, nanoplatelets and nanosheets also increases in discrete steps, even though these nanocrystals are not atomically precise. Okay, you know what? Maybe just to, I feel bad going backwards, but I want to go backwards a little bit. Maybe just to finish a point on here, where they said that these magic size clusters grow in discontinuous and quantized fashion in discrete jumps from one magic size to the next. Okay, so maybe we can extend this diagram down here. So I think what they're saying is, let's draw our own diagram. Let's draw our own second diagram here. Let's see how well this is going to work. Let's get a different color. So let's say, for example, that you had a non-classical energy profile, which looked kind of like this. So instead of just having one dip, we now have 1, 2, 3 dips. So this now in this energy system, in this energy landscape, which obviously I just made up, yeah, there's 3 different magic size clusters that you could get. So there's a magic size here, there's a bigger magic size here, and there's a biggest magic size here. And if it gets bigger than this, it just turns into a bulk crystal, like a large crystal. So it's not going to be nano anymore. So what they're saying is you get these quantized jumps. If you're watching the size of the particles as the particles grow, you suddenly get these, you go from nothing, you suddenly get this jump to the first magic size, then you get a jump to the second magic size, and then you get a jump to the third magic size, but you never see particles in between. So you never see it kind of in between those magic cluster sizes. It's always one or the other until it gets to the point where it's going to roll all the way down the big hill and become a large bulk crystal. So I think that's the idea of this quantized jumping. That's what they mean, quantized jumping between sizes. So obviously in reality, it can't, the atoms can't suddenly appear there. The atoms must come in from somewhere, and that can't all happen at exactly the same moment. Yeah, for some definition of moment, it can't all happen at the same moment. So there must be, even though it looks like quantum jumps, there must be some that, it must take some amount of time. There must be some finite time there that it takes. But maybe I'll come on and talk about that later. That might just be a limitation of what we can actually see, how quickly we can detect the different sizes here. All right, I'm going to skip a little bit, and I'm going to come on to section 2.1 here, which is the challenge of unambiguous identification of magic size clusters. Okay, advancing the understanding of fundamental principles governing quantized growth and a higher metastability has been hindered by lack of accessible characterization tools capable of reliably and accurately probing MSCs in their native environment, i.e. dispersed in liquid media. So yeah, they're mainly talking about liquid phase nanoparticles here. Now, this is a point I've made on maybe some previous streams, that looking at understanding nanoscale stuff is hard. Yeah, it's very, very small, and it's very difficult to observe these things in a way that we could observe larger objects. So there's a whole range of techniques which we use to try and peer into this nano world, but all of them kind of have limitations, some difficulties. But they're going to discuss some of them here, yeah, which is, this is a nice section, I think. The opportunities and challenges regarding the characterization of MSCs have been recently reviewed in this paper. Could be worth looking up, guys, who concluded that the combination of different techniques and the use of in situ characterization tools such as optical spectroscopy, small angle X-ray scattering, extended X-ray absorption fine structure (EXAFS), and pair distribution function (PDF), which are kind of like a diffraction technique, analysis is indispensable. So it's not just one technique that you can use just to look at this stuff. You need a range of techniques, and that means you need to understand a range of techniques, what the advantages and disadvantages of each one is, and how they can combine together, how you can kind of synthesize the information that comes from that into one overall conclusion. And that's the difficulty, I think. That's the challenge of a lot of modern material science, a lot of modern chemistry, is that there's lots of different analytical methods that we use routinely, and we have to understand how they all work in order to design experiments well, design studies well, reach good conclusions, reach correct conclusions, and not kind of misinterpret stuff. Anyway, they further argue that in situ optical spectroscopy is one of the most promising tools because MSCs are characterized by very narrow absorption peaks which redshift in discrete steps as the MSCs grow. Given the exact composition and structure of MSCs is rarely known, this reasoning has led to widespread practices of referring to MSCs by their lowest energy absorption transition. For example, CDSE418 for a cadmium selenide MSC displaying a band edge absorption peak at 418 nanometers. Okay, super interesting. So the 418 here is not the number of atoms, which you might think, which maybe I thought. It's actually the wavelength of absorption of that particular nanocrystal, and they don't know how big the nanocrystal is. That's pretty interesting. So they're describing it by kind of some proxy, really, some property of it, the absorption edge, rather than its actual structure itself. Very interesting. As a result, MSCs are typically identified solely based on their absorption spectra, often using the observation of quantized growth to support the assignment. We would like to hear strongly caution against this practice. Okay, very interesting. As sharp and discrete absorption transitions are also spectral signatures of ultra-thin 1D and 2D nanocrystals. Further, as we will discuss below in more detail, spectral changes do not necessarily reflect a change in the MSC size, as they may also be induced by changes in surface chemistry, isomerization, or conversion of MSCs into other magic-sized nanostructures such as nanowires and nanosheets. It is thus possible that similarity of absorption spectra of MSCs and ultra-thin 1D and 2D MSNCs, magic number nanocrystals, has led to the misidentification of the absorbing species in reports employing absorption spectroscopy as the sole characterization technique. Okay, love it when they do this in papers, to be honest with you. Kind of calling out what they see as bad practice, less good practice, not ideal practice. And I think, to be honest, we kind of need more of that across science in general. We need to say, you know, if the methods people are using are wrong, we should say the methods that you guys are using are wrong. You know, that's the way that science advances, rather than, you know, worrying about people's feelings, worrying about how they're going to react to the fact you call out their interpretation is questionable. If you don't do it, then people keep using bad methods. So I like that. Yeah. So here they're showing some of the, they're showing some optical spectra, which we were discussing before. So you see these series of peaks here, which correspond to transitions between electron levels, as we saw up here in our kind of diagram. These transitions between electron levels, and that will change depending on the size, and so the energy of those transitions changes depending on the size. But as they also highlight, it could be dependent on lots of other things: the surface coordination, the surfactants, the shape of the particles, all sorts of other things as well. So that's I think that was a very interesting section there to kind of call out the some practice which I think is a little bit questionable. The use of multiple techniques is thus essential to allow reliable distinction between different magic-sized nanostructures. However, combining different characterization techniques does not necessarily ensure unambiguous assignments. For example, mass spectrometry has been often employed to determine the composition of MSCs, e.g. this 34 or 68 atom cluster of cadmium selenide, but its accuracy and reliability have been questioned by several groups because the same mass fragments can be observed from colloidal quantum dots regardless of their size, or from a bulk material upon laser ablation, suggesting that they are merely the most stable fragments of the 2-6 semiconductor in the gas phase. Furthermore, mass spectrometry is not always conclusive due to heavy fragmentation of the MSNS originally present in solution. Okay, so mass spectrometry is where we ionize the material and then measure the mass to charge ratio of the ionized fragments, or the ionized let's say fragments, ionized fragments, and from that you can work out the mass of the different fragments that are present, or you can infer the mass. But they're saying, that could be reasons why that's not a good method either. We thus advocate use of transmission electron microscopy, TEM, as a companion technique to lift ambiguities in assignments based on absorption spectroscopy, as it allows a straightforward distinction between 1D and 2D, even if only because the latter are typically too small to be clearly observed in the transmission electron microscope. Okay. TM is often deemed inadequate for these purposes due to the weak contrast, poor resolution, and high electron beam sensitivity of magic size clusters owing to their small size. Moreover, drying and aggregation effects make the interpretation of the images difficult. We acknowledge these challenges, but argue that they may be mitigated by judicious work protocol and the use of advanced instruments allowing lower electron beam doses. Furthermore, recent advances in the field of high-resolution cryo-TEM make it possible to image these nanostructures directly in their native environment. Okay, really good section there. I think super interesting. Kind of critical comparison, and that's often a very important feature of perspective articles, review articles. Critical comparison of different methodologies here, and we have a great example of that, I think, in this section. They're talking about different methods that are used to measure size of things, the advantages and disadvantages of each one. They're making arguments of what their preference is. So it's not perspective. A review doesn't have to be completely dispassionate, account of the facts. You can give your own opinion, and they've definitely done that here. They said that they like to use TEM as a complement to optical absorption spectroscopy and mass spectrometry, other methods as well. TEM is a microscopic technique. It shows you images of the particles themselves, and yeah, I think they make a good argument that TEM should be part of this kind of suite of analysis that you would do here. They talk about some of the disadvantages of TEM, but point to some maybe ways that those disadvantages can be overcome. So a really nice section. I really kind of like what they've done there. The composition and structure of these these magic-sized clusters is known only for a few cases. Nevertheless, there is evidence that ligands bound to these clusters have a decisive impact on their stoichiometry, structure, and stability. X and Z type ligand, i.e. negatively charged and electron paired donors such as carboxylates and metal ligand complexes respectively, lead to non-stoichiometric magic-sized clusters, likely due to charge neutrality requirements. Okay, so when you have a semiconductor or compound, they're saying that the magic-sized clusters are often non-stoichiometric. So for example, cadmium selenide, you're expecting the bulk to have a 1-to-1 ratio of cadmium and selenium, but in the magic-sized clusters they don't, and that's because of the influence of the charge of the of the ligands on the surface. In contrast, neutral L-type electron pair donors, such as amines and phosphines, seem to favour stoichiometric 2,6 MSCs, although the exact structures of these species remain elusive. Considering the very high surface to volume ratios at MSCs and the hybrid organic-inorganic nature of colloidal semiconductor nanocrystals in general, the crucial importance of ligand capping layer is not surprising. However, the mechanisms through which the ligand influence is exerted have not yet been fully elucidated. Again, really nicely written section. So introducing the idea of stoichiometric and non-stoichiometric clusters, and the fact that when you have charged ligands, that can lead, or often does lead, to these non-stoichiometric magic size clusters, which they give some examples of here: cadmium, zinc, selenium, sulfur, sulfide, selenide, telluride. These have been extensively studied, they say here, back to the 1980s. Or stoichiometric, where you have neutral ligands on the surface, and it gives some nice structures, some calculated structures, I think these are, of some of the magic size clusters. You can see pretty interesting structures here. I mean, it's good to actually look at these things, isn't it? We haven't really looked at structural pictures of them. We've kind of had electronic structure pictures, but not atomic structure pictures. Well, we have some of those here. So yeah, there we go. We have this idea of non-stoichiometric and stoichiometric materials as well. We talked a little bit about classical nucleation theory and non-classical nucleation theory, and the article will go on. We're going to skip through a lot of this now, discussing optical absorption, discussing small angle X-ray scattering, which is a very powerful technique for looking at small particles, things which don't have large crystalline domains. X-ray scattering, X-ray diffraction is normally used for very crystalline materials. These are looking at particle sizes of things which are less crystalline, perhaps. Oh, so sudden change in the music. And then they go on to talk about formation mechanisms. So we don't have time to go through the whole article, but there's a lot of really interesting stuff on here, and I will leave you guys, if you are interested in this. As I said, this is an open access article. Anyone in the world can read this, but hopefully what we've got from this stream today is a little bit of an introduction to the field, introduction to why these materials are interesting, some of the kind of pertinent issues that are bound in this field. And if you're looking to get into this field, if you're just interested in nanoparticles and nanoscience in general, this is a really well written perspective article. Nice to see the kind of critical comparison, the actual opinions being expressed about the best way to do things, the best way to analyze things, the best way to understand things. Really nice paragraphs here about how to understand atomically precise clusters. And I thought the introduction really nicely written as well. I think our additions are useful additions to this diagram. They could find a place there. It'd be nice to extend this diagram in both directions, just to place it a little bit more in context. But yeah, great article. We don't have much time to go through more of it, but yeah, you guys can pick it up yourselves. ! Paper will work in the chat until I change it. So even when we go offline, you can still ! Paper to get the link for the article until the next stream, when it will be changed to the next one. Or if you want to follow us on Twitter, you can do that, and then we tweet out the articles that are being discussed. So you can always find a record of the previously discussed articles there. All right, we're gonna wrap up. But thanks so much for joining us. If you're joining us live on Twitch, thanks very much. You can always hit that follow button down below. That will alert you next time we go live, so you will always know when we are streaming. If you're watching on YouTube, or if you're watching on a VOD later on Twitch, then follow us on Twitch. Head over to Twitch, follow us there, or follow us on Twitter, and you'll know when we're going live. Try and catch the stream next time live. It's a little bit more fun, a little bit more interactive that way than watching on YouTube or on the VOD on Twitch. So it'd be great if you can join us next time. But thanks for coming. Thanks for being part of the stream, whether you're watching live or watching the recording. thanks for being part of the stream, and thanks for being part of the Journal Club. And yeah, any suggestions for papers you would like to review? If I feel competent to review them, I would love to take suggestions, and that might feature on a future stream. All right, we will wrap up there. Thanks for joining us. Have a good day wherever you are, and I will see you on the next stream. See you later.